Okay, welcome to this doctoral meeting. Thank you for being here. Today, Soutullo is going to talk about a method for lossless range image generation and reconstruction from spinning 3D LiDAR point clouds. Thank you, and after his talk, we will have time for questions.
Well, first of all, thank you everyone for being here today. This doctoral meeting will have mainly two parts. First of all, we'll talk about LiDAR sensors, what they are, why they are so cool, and so on. And then we'll focus on a specific problem we solve as a part of my PhD thesis, which is this whole missing points mystery and information loss problem. So let's get started. First of all, if I had to define what LiDAR is in a single sentence, I would say LiDAR is a sensor that allows machines to see in 3 dimensions. So what do I mean by this exactly? First of all, we need to understand that to safely navigate the environment, robots and cars, for example, need to understand their surroundings. So they need to be able to answer questions like, where am I? What is around me? How far is that obstacle? Is it moving? So for example, here this car, in order to navigate the road, needs to know where the road is, of course, if there are other cars around, if there are any pedestrians in the middle, and stuff like this. So our first guess as how to solve this problem would be probably just put a camera on the car and let it identify objects. And this works fine as a first approach because cameras capture the world in 2D dimensions, so we are able to see that there is a tree here, of course. It has some nice advantages. Well, first of all, I don't mention it here, but cameras are really cheap nowadays, which is a huge advantage. But besides that, they provide rich color and texture information, which is really nice to identify objects. But they have some disadvantages as well. They need external light, which is not a big problem. You can provide light, and there are night vision cameras anyways, so this is a problem, but not a major problem. They are sensitive to shadows and glare, meaning that if in a scene you have like a very dark area and a very bright area in different parts at the same time, it's very difficult to capture details from both at the same time. That's a bigger problem, but crucially for this talk, they don't provide depth information. So here we have no way to tell whether this tree is really far away or small. Like you don't have this distance measurement. And so the first approach to solve this problem that you might think of is just use 2 cameras to mimic the human vision. Like this is what 3D cinema does essentially. And yeah, this works. You just have to match the corresponding pixels from both cameras and then triangulate the depth from both of them, and you can get like an estimate of the distance to the scene you're recording. The problem with this approach is that first of all, it's computationally heavy. You have to match all the pixels, which is not trivial. And it fails on textureless surfaces, meaning that if you film, for example, this wall, this is completely white, so there's no way for you to tell which pixels match exactly which, because all of them look the same, all of them have the same colors. So, sorry. It is very difficult to match, and therefore the depth prediction will be inaccurate. And actually, on top of that, the accuracy drops drastically with distance. So this setup works fine in a room like this, but if you want to be able to perceive distance in 100 meters, it's not going to be sufficiently accurate. So this is critical for autonomous cars, of course. So if we had to make a wish list for an ideal sensor for an autonomous vehicle, which is what we are going to focus about today, it should have these characteristics. First, we should have precise depth information. We need to know whether this obstacle is like 100 meters or closer, and if possible with centimeter level accuracy. We should be able to see in a long range because we are driving a car, and 100 meters is nothing in terms of time if you are driving a highway, for example. So ideally 100 meters and away would be nice. And it should have also high resolution, meaning that we should be able to resolve twin objects, distinguishing poles from pedestrians and stuff like this. And the question is, can we have all of this in a single sensor? And the answer is yes, of course we can. And we have it here. This is a LiDAR sensor, and I will show you how it works, basically. I have here a software that allows us to visualize what the sensor sees. And now I will point this at you, and the laser will burn your retinas. No, I'm kidding, it's fine. Yeah. So this is what we see, what is pretty that. But here you can see the front seats. Maybe you can see some picture here, I don't know. Yeah, here we can see ahead. I promise you this screen looks better. Here it's very difficult to see. This is like the right wall. Yeah. I mean, you can distinguish the seats, right? Yeah. I promise in this screen looks weirder. Okay, so this is what the sensor essentially is like, a set of points in 3D space. And now we'll talk about this in more detail. Yeah, okay, let's turn this off and then go back to here. Alright, so what we just seen is this sensor here. They are exactly the same model actually. And this is a solid state sensor, meaning it has no mechanical parts moving, which is an advantage because it's more simple, but it has a limited field of view. As we have just seen, it only measures in a cone view. You only see this part of the scene. On the other hand, we have spinning LiDAR sensors, which are more commonly used in autonomous vehicles, because what they have here is this head that rotates around. The lasers are here and here, basically, and this head spins around like this. So basically, it is able to see 360 degrees field of view by rotating physically, which is really nice for autonomous vehicles because we want to be able to see all around us, not just in front of us. So in this work, we focus on spinning LiDARs, which are these ones here, as I said. So let's see, first of all, how it works, what we have just seen. And the analogy is very simple. A laser meter, I think we all know what a laser meter is, I guess. Like some construction workers are using them instead of measuring tape, they just use like a laser like this. They point the laser to the wall and then they see the measurement on the screen basically. And this is the same principle of the LiDAR sensor. So the way this works is very simple. The laser meter essentially sends a light pulse to a wall. The light pulse gets reflected back. And if we measure the time that it takes to reflect back, using this very simple equation here, which involves the speed of light, of course, we are able to estimate the distance. And a LiDAR is just essentially a bunch of these bundled together. So we have many lasers doing many measurements at the same time. So if we measure here, 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 and here, we know something is on all these positions at the same time. So we probably know a wall is present here. That's the basic principle. And for example, this LiDAR sensor here, which is really commonly used in autonomous vehicles, just to give you an idea of a real sensor, this one here has 64 lasers stacked vertically, like in different angles, like this, like this, like this, like this, like this. And then what it does is that it rotates 10 or 20 times per second, depending on the configuration. And then they fire each laser thousands of times per revolution. So in general, around 2,000 times per revolution. And so the result is like a dense scan of the environment that looks like this. So this is a real frame from a dataset, the Kitty dataset, which is really famous. Here in the center we have the car, of course, and the car has, like on the roof, they installed this LiDAR sensor. And basically it captures the scene like in a circular fashion, like because it rotates. This is why we see here that the points tend to form these rings. Each of these rings corresponds to one of these 64 lasers that I talked about before, and as they spin around, they capture the scene. So here we can see that maybe there's a park here there are some walls, this is probably the road, here another road, and so on. So essentially what we got here, and this is the important takeaway, is a collection of points in 3D space that in the particular case of spinning LiDAR sensors tend to form these rings because of how the sensor works. So as I said, this is what we call a point cloud, which is, as I mentioned before, an unstructured set of X, Y, and Z coordinates in a 3D space. And this is really nice. It contains a lot of information. We can actually infer a lot of things from here. But it has a major problem, which is that it is a lot of information. It is very good information, but it is too much. And what I mean by this is that these sensors actually produce millions of points per second, which makes it very difficult to process in real time. Like a self-driving car needs to perceive the environment and make decisions instantly, basically. And so if you are receiving millions of frames per second and you need to process them in a maybe not so powerful computer, this becomes a problem. And there are many ways to to like fight with this problem, but we will focus on one of them, which is using range images, which is a way to process these point clouds more efficiently. And basically, the main idea is very simple. You just create like this panoramic image around the sensor, where each row, well, this is meant to represent an image, and each of these squares is meant to represent a pixel of the image, okay? And essentially, you map each row of the image to one laser. So in the previous case, we'll have 64 rows in the image because we have 64 lasers. And we map each column of the image to one of these 2,000 samples per revolution, right? And on each of these pixels, you store the distance to the corresponding point. So this pixel here would store the distance to this point here. This pixel here would store the distance to this point here, and so on and so forth. So each pixel corresponds to a specific laser direction, and the pixel itself stores the distance to the point, to the corresponding point. And the results looks something like this. This is the panoramic range image. Here we have from 0 to 360 degrees, the horizontal field of view. And on this axis, the vertical axis, each row corresponds to one laser, as I said before. So for example, this we can see here like a gun here, some electric poles, and the colors of the pixels represent the distance. So this dark magenta means this point here is really close, whereas this blue pixel here means it's more far away, and this green one means it's really far away. So essentially we have like a depth image, basically, that we created from the point cloud by using range image. And so the typical pipeline when using this is to, well, first we start with the 3D point cloud because that's what the sensor provides. We have just seen that. As I said, since processing this directly, it's computationally heavy, what we do is that we project it to 2D, and we get this image. And then here we perform whatever we want to do. Like maybe here we want to detect pedestrians, we detect them here in this image instead of working in 3D space, which is more computationally heavy. So we perform our task here, like the object detection or whatever. And then when we're done, we project back to 3D to get the original point cloud, but with all the elements identified in 3D space, which is what we want at the end of the day. So basically we are using range images as intermediate representations to facilitate tasks computation. That's the main idea I want to convey. These are just intermediate representations of point clouds that allow them to be processed more efficiently. If you understand that from range images, that's enough. So now, here you might ask, well, this is too good to be true, right? Like we are going from 3 dimensions to 2 dimensions. Do we really keep all the information? Because it sounds too good to be true. We are just dropping 1 dimension, just like that, going from 3D to 2D, and you're telling me we are not losing any information? Well, the answer is that with a perfect LiDAR sensor, an ideal LiDAR sensor, this holds true, because the mapping is bijective. This is because, well, it's just a mapping between Cartesian and spherical coordinates. I will not go into details, but just keep in mind that it's a bijective, meaning one-to-one perfect projection, which means it's a lossless projection, a projection where no losses occur. And yeah, with a perfect LiDAR sensor, this holds true. As we can see here, each point that we project to the image falls exactly on the center of its pixel, and all of them fall perfectly in the image. But with real LiDAR sensors, this does not occur. Basically, the main reason is that real LiDAR sensors have laser beams originating from different physical locations. What do I mean by this? It is physically impossible to put 64 lasers exactly on the same position because, well, they have some volume, they collide with each other. So you need to put one laser here inside the sensor. You need to put one laser here, over here, over here, over here, and so on, so that they don't collide with each other. And what this causes is that when you make this projection, the points do not fall in the center of their pixels. Instead, they look wobbly and messy, like this, essentially. Because like the circles we've seen before, they are not perfectly circular anymore, they are eccentric. So, well, yeah, this introduces this problem when projecting the points to the range image. We can see here the points are not in the center of their pixel, and some of them actually, what happens is that they go to other pixels even. This red point here should have fallen in this one, but it's falling in this one. And so now we have a problem where we have 2 points in the same pixel, which is problematic as we'll see now. So what happens? What are the consequences of this? Well, first of all, of course, as you can imagine, since points are not centered in their pixels, we got geometric errors, meaning that when we go from 2D back through 3D, we won't recover exactly the original point cloud, because we assumed the points would be on the center of their pixels, but they're not. So this will introduce some mismatches. And even worse, when 2 points map to the same pixel, we can only keep one of them, because each pixel can only store one value in principle. So we will incur in data loss, which is even worse. And so, of course, the question is, do people just accept this? How do people deal with this problem? And actually, some of them just ignore it, accept the loss as noise, and yeah, works. It's simple. And well, this works because, like, in general, the loss is not that big. We're talking about maybe each point moves a couple of centimeters, and we lose 8% of points. It's acceptable for some scenarios. What other people do when they need more precision is that they just increase the resolution of the image we've shown before. So if you make the pixels smaller, it is less likely that 2 points collide on the same pixel because they are smaller. And well, distance to the center of each pixel is also smaller, which means you have less geometric errors in general. And this works fine, but it's more computationally expensive, of course, because you have to store more pixels, and it doesn't solve the underlying geometric problem, which is more important. And the actual solution is that if we know the exact topology of the sensor, meaning if we know the laser of beams, the number of samples per revolution, the elevation angles, the spatial offsets, like if we know exactly how the sensor looks, how it's constructed, how the lasers are positioned, all these tiny offsets and the angles and so on, which are named the intrinsic parameters of the sensor, which, as I say, describe the sensor topology. If we know all this, we can do proper projection, which, with like using some basic trigonometry and math, we can ensure that we always map the points to the center of their pixels, which means that we won't have more geometric errors or point collisions, which means perfect lossless range images. So yeah, we can leverage these parameters, as I say, to using basic trigonometry to do this. So this begs the question, of course, why isn't everyone doing this? And it boils down, I would say, to these 3 main problems here, which is, first of all, these intrinsic parameters, the ones that I just described, are often not published in datasets. Like many datasets just provide you with the 3D point clouds, and that's it. They don't give, like, they provide maybe the sensor model, but the thing is that even with the sensor model, each sensor might have different intrinsic parameters, so this is not enough. So in general, well, not in general, but in many scenarios, intrinsic parameters are not provided, not available. Sensor variety is another problem. Like, even if you have these parameters, every manufacturer uses a slightly different model, so like a slightly different way of using these parameters, so this is also a problem. And complexity, like even if you have these 2, imagine you have the intrinsic parameters and the manual on how to apply them, you have to make the code to use them, you have to learn how it works, and actually it's a very tedious process, which for a couple of centimeters of accuracy people just don't do many times. So our take here is that we need a general automated way to find and apply these parameters. If we simplify this process and make it general, maybe people will start to use this and to make proper range images and projection. So this is what we propose, basically. This is the main work of my thesis at the moment. And yeah, it's named Alice LRI. And basically it is, well, as the name comes from these initial letters here, automatic LiDAR intrinsic elevation estimation for lossless range images. And our starting hypothesis, essentially, is that the point cloud itself, the 3D points, just alone, contain enough information to recover the intrinsic parameters of the sensor. So our goal is to automatically infer these parameters given the point cloud, and these parameters are, as I mentioned before, things like the number of lasers, samples per revolution, beam angles, spatial and angular offsets, and so on. And as I said, the method needs no metadata, no information at all about the sensor, just the point cloud. And the result is a sensor agnostic method to generate lossless range images. So let's see how it works, basically. And first of all, what we need is that we need to propose a unified model for spinning LiDARs, because as I said before, each manufacturer has a slightly different way of using these intrinsic parameters. And well, I will not go into many details here, but this is the model that we propose. There are many equations here, but they are not so difficult. It's just mostly trigonometry and spherical projections. What you need to understand from here is that the blue ones, the blue values here, are the ones that are directly provided by the point cloud. So, I mean, each x, y, and z coordinate, the distance to each point. These things, the blue ones, we can extract directly from the point clouds, trivially. And then the red ones are the intrinsic parameters of the sensor, which are unknown to us. And this is the red ones is the ones that we need to estimate. And the yellow ones are just intermediate variables that combine both. So the main takeaway here is that we have the blue ones, and we need to estimate the red ones based on the blue ones. And yeah, estimating this is non-trivial because, well, there are many solutions. First of all, you don't even know the number of parameters, because the ones here that have an L on top is like 1 for each laser, and you don't know how many lasers you have. Like, this L parameter is the number of lasers that you need to estimate as well. So, like, if this L is, for example, 64, then you will have 64 of each of these ones. But if this L is 100, then you'll have 100. So you don't even know, like, in advance how many parameters you have. Estimating this whole thing jointly is non-trivial. And our solution is an algorithm that estimates this. I will not go into details because we don't have time for that. But basically, the way it works is through an iterative consensus-based process that leverages the half transform. The people that work in computer vision might resonate to them this method. And then basically iteratively refines the estimates, and well, it uses a tracking mechanism to ensure consistency. Summary, at the end of the day, we input the point cloud to this algorithm, and it outputs these parameters, the values of these parameters. And so the result is a complete accurate sensor model, inferred purely from the point cloud data, which is what we want. From the point cloud, we now have a inferred like sensor topology, basically. And well, once we have the parameters, as I said before, we can match each pixel to each point to its exact pixel location, and we can project perfectly back to 3D, so we can generate these lossless range images. And we'll see some examples now. We'll see some results. So this is the standard projection that everyone uses, and this is ours. There are some highlighted areas that maybe you cannot distinguish, but if we zoom in one of them, we see that the standard projection method here, there's a missing row. This missing row is there because actually what happened here is that 2 points collided in the same pixel, so this whole row was, well, like this whole row was mapped maybe to this one or to this one, or vice versa. And so we couldn't keep both of them. And this is why the information here is lost, because of the standard projection method that I talked about in the beginning, whereas our method keeps all the details. Beyond that, when we back project to 3D, the standard projection method has the same limitations, like there are some points here that are missing, especially in these lines here, whereas our method Alice perfectly reconstructs the 3D point cloud. If we go to more quantitative measurements, the standard approach in the Kitty dataset, which is a very famous dataset, on average loses 8% of the points, which is a significant number. So what people do usually, as I said, is that they increase the resolution. In this case, if we double it, we drop the loss to 0.52, which is acceptable. But the thing is that even if you increase the resolution to crazy values like this one, which is multiplying 32 on each dimension, you still lose something. Like, this doesn't fix the problem. Whereas our method loses nothing, because it makes a perfect projection, as I said, by inferring the intrinsic parameters. So essentially you have like the benefits, the precision benefits of having infinite resolution, I would say, you could say, infinite resolution, but using the native, the minimal resolution. So yeah, you have the best of both worlds, like precision and computational accuracy. And we tested this through the whole data set, which involves this number of clouds, and yeah, basically 0% loss on all of them, and no points were ever lost during the reconstruction. And to also show that this works like for things that, well, other people use, we took an existing point cloud compression algorithm which uses range images as intermediate representation. Well, it's this algorithm here, RTST. And the experiment consisted on replacing their standard projection method with Alice LRI. Essentially, we just change a function of the code they provided. And instantly, you can see that the algorithm improves significantly. Essentially, this axis here represents the point cloud quality, and this one the compression ratio. And basically, we can see that just by replacing the projection method with ours, in general, you get more, well, you get higher compression for the same quality, basically. That's the main takeaway. And yeah, that's all I have to say. So, as a summary, we discussed the real LiDAR sensors have beam offsets and other non-idealities that render these projections problematic when we use range images. Standard workarounds work fine-ish, but they are not perfect. They are suboptimal. And so we achieve we created a method that automatically infers the sensor topology from a point cloud, and this allows us to create these projections perfectly without no error, combining the best of both worlds, and it works on any spinning LiDAR sensor without metadata or calibration files. And yeah, that's all I have to say. Thank you for listening.
Do you have questions for someone?
I have a question.
Okay.
It's only to break the ice. Okay, I know that I know your work, but the idea is how do you incorporate this to an autonomous vehicle? Because you have to the processing for getting the parameters of the LiDAR sensor, you can get it once,
yeah,
and then apply, but maybe the sensor with the movement, these parameters can modify. I'm being, if you need.
Yeah, I understand your question. Yeah, with the usage of the LiDAR sensor, the parameters can drift, but this won't affect projection because what causes this mismatch here, let me show you. Yeah, what causes this wobbly scanlines problem is not the physical positions of the lasers per se, but the factory calibration that they do in order to compensate for this. So even if the beam positions move as you use the sensor, these curves will look exactly the same each time because they are we are reverse engineering what the factory calibration did. We are not inferring what the actual positions of the beam laser are, basically, because you cannot know those because the sensor only provides XYZ coordinates based on the factory calibration, not based on the real positions. The sensor doesn't know its real positions. It only knows its factory calibration positions. I don't know if that answers your question. Yeah. Yeah.
Have you quantified how much computational power you need to do your computation?
Yeah. Well, in the paper, which is this one here. Sorry, let me. Where was it? Here, yeah. Yeah, I haven't talked about this today, but in the paper we have a runtime performance analysis. Just to give you a rough idea, to estimate the parameters, we run this on a workstation, like a regular PC. We haven't tried in different edge computing things or whatever. But just to give you a rough idea, estimating the parameters takes about 30 seconds given a point cloud, which sounds like a lot, but remember you only have to do it once per sensor. Once you do it, you can reuse these parameters, you can save them and reuse them. And then the important part, which is the intrinsic aware projection and back projection, this runs in the order of 10 milliseconds each part. So it's feasible for real time because if you work with LiDAR sensors, you know typically the real time threshold is around 100 milliseconds because usually these sensors take 10 samples per second. So basically the method works for real time. Yeah.
So you use it, for example, in a car?
Yeah.
This could be part of the warm-up.
Yes.
The startup of the
exactly.
car.
You can do it. Maybe you can do it. I don't know. You can do it once, and then store it in a memory. If it gets deleted for some reason, do it again. It takes 30 seconds, and then after that, you can reuse it, basically, and it works in real time. Yeah, thank you.
Any other question? Okay, well, thank you.
Thank you.
Thank you.